Draw a circle on a grid of dots, count the dots inside, and you've basically just measured pi. That's the whole trick, and it sounds too easy, so let me actually show you. Here's a grid where every dot sits at a whole number spot, 1 over, 2 up, that kind of thing. Now I drop a circle down, centered on one of the dots, and I just count how many dots fall inside it. Watch the number climb. For a circle of radius 10, you get around 317 dots, and the area of that circle, pi times 10 squared, is about 314. Those two numbers are shadowing each other. Make the circle bigger, count again, and the dot count keeps chasing pi times the radius squared. So a pile of dots, no curves, nothing round about them, somehow knows about pi. I think that's a little bit magic, and the reason it works is genuinely deeper than it looks. So let's actually pull it apart and see why the dots care about a circle at all. Let me pin down exactly what we're counting, because being precise here is where it gets interesting. Put the center of the circle at the origin, the dot at 0, 0. The dots are all the points with whole number coordinates. Mathematicians call this the integer lattice. And honestly, the name lattice makes it sound fancier than a sheet of graph paper. We pick a radius r, and we count every lattice point whose distance from the center is r or less. A point at coordinates x, y is inside when x squared plus y squared is at most r squared. That's just the Pythagorean theorem doing crowd control at the door, letting in only the dots close enough. Call that count n of r. So n of 5 means every dot with x squared plus y squared, no bigger than 25. There are 81 of them, if you're curious, and the claim we're chasing is that n of r is close to pi r squared, the area. The question that'll eat the rest of this video is, how close is close? Because the answer is one of those problems that's been open for 200 years. Here's the picture that makes the whole thing click, and I wish someone had shown me this one first. Give every dot its own little 1 by 1 square centered on the dot. Each square has area exactly 1. So if you count the dots, you've also counted the total area of all their squares, because dots and squares are the same count. Now those squares roughly tile the inside of the circle. The number of dots is about the total area of the squares, and the total area of the squares is about the area of the circle. That's the bridge. Dots become squares, become area, becomes PIR squared. It's almost a proof already. The only sloppy part is right at the edge, where the squares poke out past the circle, or the circle bulges past the squares. In the middle, everything tiles perfectly and cleanly. All the action, all the error, all the hard math for the next 2 centuries. It all lives in that thin, ragged ring at the boundary. Keep your eye on that edge, because that's where the real fight is. So the dot count is the area plus some error from that ragged edge. Let's actually look at the error and see how it behaves, because it does not behave. Define E of R as the real count minus PIR squared. If the count were perfect, E would just sit at 0 forever. It does not sit at 0. Watch. As I slowly grow the radius, the count jumps up by a whole chunk every time the circle swallows a new dot, sometimes several dots at once when it crosses a symmetric point. But pi r squared grows smooth, no jumps. So the error is this jittery thing, bouncing above and below 0, never settling. Sometimes the count runs ahead of the area, sometimes it lags behind. It's like the dots are trying to approximate a smooth curve using nothing but stairs, and the mismatch never fully goes away. It just sloshes around. And the natural question, the one Gauss asked, is, okay, it wiggles, but how big can the wiggle get? Is it under control, or can it blow up on us? Gauss got the first real answer, and his idea is the square picture from before, just taken seriously. Every dot inside owns a unit square. Those squares all sit inside a slightly bigger circle, and they all cover a slightly smaller circle, because a unit square only reaches out about half of the square's diagonal from its center, roughly 7/10 of a unit. So the true area is trapped between 2 circles, whose radii differ by less than 1. The gap between those 2 circles is a thin annulus, a ring, and its area is basically the circumference times its width. Circumference is 2 PIR, width is a small constant, multiply, and the error can't be bigger than something like a constant times r. So E of r is at most on the order of r. The error grows, sure, but only as fast as the perimeter, while the count itself grows like r squared, the area. Compared to the thing you're measuring, the error is shrinking. That's why counting dots gives you pi more and more accurately as the circle gets huge. And that's where it stops being a homework problem and starts being a 200-year headache. Gauss showed the error is at most about r, but is that the truth? Or was he just being generous? Because here's the thing. The error probably doesn't actually reach the size of r. All those spikes above and below 0 tend to cancel each other out. And the boundary dots don't all pile up on one side. The real error looks a lot smaller than the perimeter bound suggests. So the game becomes, find the true exponent, write the error as roughly r to some power theta. Gauss's bound says theta is at most 1. The question is, how far below 1 can you push it? Every time someone shaves that exponent down, it's a real event. In this corner of math, papers get written, records get broken. It's basically a very slow, very nerdy world record that's been going since the 1800s. And nobody has finished it. Let me show you how low people think it should go, and how low they've actually managed. First, how low can we even hope to go? There's a floor, and Hardy found it. The error can't be too small, because those dots near the boundary genuinely bunch up sometimes. Think about it. When the radius squared happens to be a nice number that's a sum of two squares, in lots of ways, a whole bunch of dots land exactly on the circle at once. The count lurches, so the error keeps getting kicked. It can't just quietly decay to nothing. Hardy proved the error is not smaller than roughly the square root of r forever. Infinitely often it gets at least that big. So theta can't be less than 1/2. That gives us a hard floor at 1/2 and Gauss's ceiling at 1. The true answer lives somewhere in that gap. And the strong conjecture, the one most people believe, is that the floor is basically the truth. The error should be about the square root of r, give or take a tiny bit. So the guess is theta equals 1/2. Beautiful, clean, and completely unproven. So here's the actual scoreboard, and it's kind of hilarious how hard won every inch is. Gauss started at 1. Then in the early 1900s, people pushed it down to 2/3, using clever ways of counting the boundary dots. Then 2/3 got shaved to a little less, then a little less than that. The exponents get ugly fast. Fractions like 46 over 73, then stuff with hundreds in the denominator. The current record is around 0.629 from Martin Huxley, built on a mountain of technical machinery about counting points near smooth curves. And remember, the conjectured answer is 0.5. So after 200 years of some of the sharpest people in the field grinding on this, we've gotten from 1 down to about 0.63. We are stuck, a tenth of the way, an eighth of the way from the finish line, and it will not budge. The last stretch from Huxley's number down to 1/2 might be the hard part of the whole problem. That gap is where the real monster is hiding. Now let me flip the whole problem, because there's a second door into it, and it leads somewhere gorgeous. Counting lattice points inside a circle is really counting how many ways whole numbers can be a sum of two squares. Here's why. A dot at x, y sits at distance squared equal to x squared plus y squared, some whole number n. So counting dots on the circle of radius root n is the same as counting the ways to write n as a sum of two squares, order and signs included. Call that r2 of n. Then the total count inside radius r is just 1 for the center, plus r2 of 1, plus r2 of 2, plus r2 of 3, all the way up to r squared. So the smooth geometric thing, area, pi, circles, is secretly a running total of a number theory function that asks, in how many ways is each number a sum of two squares? Geometry on one side, pure arithmetic on the other. And when a problem has two faces like that, you can use one to crack the other. And R2 of n has this shockingly tidy formula which I did not believe the first time I saw it. To count the ways to write n as a sum of two squares, you look at the divisors of n and sort them by their remainder when you divide by 4. Count the divisors that leave remainder 1. Count the divisors that leave remainder 3. Subtract, multiply by 4. That's it. That's R2 of n. Take 5. Its divisors are 1 and 5. Both leave remainder 1. When you divide by 4, none leave remainder 3. So 2 minus 0 is 2, times 4 is 8. And sure enough, 5 is a sum of two squares in 8 ways, 1 squared plus 2 squared, with all the sign and order flips. The reason 4 shows up is the 4/4 turns of the plane, the fourfold symmetry of the whole grid, odd numbers dividing in, split by remainder 1 versus remainder 3, secretly control how many dots land on each circle. Prime numbers are quietly running the geometry. That connection is the thing that still gives me a little chill. Okay, watch this part. This is the payoff. We said the dot count is a running sum of R2 of n, and R2 of n is 4 times remainder, 1 divisors, minus remainder 3 divisors. Add all of that up as the circle gets big and something falls out. Counting across all numbers up to r squared, how many have each a divisor of each type, turns into a sum that goes 4 times 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, on and on, odd numbers, alternating signs. And that sum, that famous alternating sum of odd reciprocals, equals pi over 4. It's the Leibniz series. So when you divide the total dot count by r squared and let the circle grow forever, the arithmetic literally reassembles itself into 1 minus a third plus a fifth minus a seventh times 4 and hands you pi. The dots didn't just approximate pi by area, they compute pi exactly as a fraction of odd numbers through the back door of counting divisors. Same pi, two completely different roads meeting in a grid of dots. So here's where we are. A grid of dots and a circle give you pi two different ways. Once through area, count the dots, divide by r squared, and once through arithmetic, sort divisors by 4s, and you land on the Leibniz series, same pi hiding in the same dots. And sitting on top of all of it is that error, the little wiggle between the count and the area, and we still don't know how big it really gets. Gauss capped it at r. Hardy said it can't beat root r. The record's parked around r to the 0.63. The answer everyone believes is root r. Exactly, and nobody can prove it. Here's the thing that actually bugs me. This is not some exotic object. It's dots on graph paper and a circle. You could draw the setup in kindergarten, and that innocent little picture contains a question that has beaten 200 years of the best mathematicians alive. The gap between what we can see and what we can prove is enormous, and it's sitting right there on the grid. Go count some dots. Tell me if you find the exponent.